we have seen a framework for process model quality. This framework tells us which parts we need to take care of in order to ensure a good quality process model. Today we're going to go a bit more into depth on one particular type of quality, behavioral correctness. This is one of the most challenging correctness notions, and what I will do in this video is show you some hints in order to verify that your model is behaviorally correct. And the first step, of course, you can take while modeling. So while writing your process model, you can take several steps to help ensure that your process model is going to be behaviorally correct. And it's a bit of a cliche, but in order to have behavioral correctness, you need structural correctness first. So they are different things, but if the model isn't according to the BPMN standard, of course it becomes even harder to establish the behavior that we need in order to verify behavioral correctness. So make sure that your syntax is all right and that the models you are writing adhere to the BPMN standard. And again, a good way to do this is to use a dedicated BPMN modeling tool that will simply refuse to draw anything that is not according to the standard. Then, keep your process model as simple as possible. Think of layout, think of decomposition. So if there is going to be a behavioral correctness check after that, you make that check a lot simpler by layouting your process model in a way without crossing arcs, without weird flowy movements, just standard from left to right, makes it much easier to read and therefore to check behavioral correctness later. If your model gets too big, that is also a problem for behavioral correctness checks, because we're going to see a divide and conquer approach, and that is helped tremendously by decomposition. So if you can introduce sub-processes in your model, then do it, because it helps a lot in verifying behavioral correctness. One thing that you can also do while modeling is avoid overusing the data perspective. It's a good idea to add the data objects and the data collections and the data stores that are relevant for the steps executed in your process. But everything you add to that on top of that data perspective makes it harder. So, and then I'm talking in particularly about hidden data variables. So the data variables that are used in the XOR split, in the OR splits, this data is hidden, and the more you use that in a non-trivial way, the harder it becomes to establish behavioral correctness later on. Also, this introduces Turing completeness, and hence it's more difficult. So a good kind of mean rule of thumb is that the modeler has to be able to prove behavioral correctness. If you're not able to do that, then probably your model is too complex already. That's a bit mean, I know, but let's see what we can do besides when you're modeling, what you can do if you're given a model that's already done, how you can establish the behavioral correctness of that model. And we're gonna look at two different settings. First one is intra-pool. So that means within one pool. So no messages, just sequence flows. And the first thing to do is see if you can make your process model smaller by introducing sub-processes. Maybe not in the way to change the model, because there might be good reasons why that hasn't been done. However, if you can do that, then you can divide and conquer your problem. So if you can prove that a sub-process is behaviorally correct, then in its parent process, you can use that and say, this is just a task. It's behaviorally correct, so there are no weird issues in that. So I know that I can look at this parent in isolation. I don't need to consider anymore what is in this subprocess. So that helps you tremendously. Another way to divide and conquer checking for behavioral correctness is to use blocks. And blocks are not really subprocesses, but that are parts of the model that we can still consider in isolation. And if that fails, then you have to play the token game. So try to violate the behavioral correctness property. So just take one behavioral correctness property and try to violate it by playing the token game. If you can get to a deadlock, then you know that you have violated a behavioral correctness property. If you have a live lock, you know that you have violated a behavioral correctness property. So by playing the token game, you can establish for any model whether it is behaviorally correct or not. However, this is difficult and requires practice. Okay, so we want to avoid having to play the token game. So let's focus on the divide and conquer approach. And in particular, I'm going to show you some tricks that you can use for block identification. So I'm going to show you some patterns then that you can follow in order to prove that certain blocks or parts of your model are behaviorally correct. I'm also going to show you some anti-patterns. If you see those, then you already know, okay, this is wrong, this model is not behaviorally correct. And by looking for these patterns, you might get a feeling for the correctness of the model. Of course, it doesn't prove anything because you can never give all patterns that would violate behavioral correctness. Let's look at this in more detail step by step. If you can identify two blocks such that these two blocks by themselves independently are behaviorally correct, and the only sequence flows going into those blocks come from the same gateway, and the only outgoing sequence flows from the blocks go to the same gateway, and the two blocks are connected by these two gateways, and these two gateways have the same type, so both XOR or both AND or both OR, and the split gateway allows both of these blocks to be reached, so there is no condition that's always false, then the connected blocks, so the entirety of this whole thing, so this is then your block, this then the outer block is behaviorally correct. A small variation on this is the loop. So notice that here we have two XORs and A is kind of, you always have to do, and then B goes back. This is also behaviorally correct by construction. This is an example of a structure that you can use in order to identify blocks and to divide and conquer your problem. So if your whole model is built up in blocks like this, you have proven that your model is behaviorally correct. Another example. If you have a block, and I've shown it here as a little cloud, and in that cloud you only have exclusive choice gateways, then your model is also behaviorally correct. And again, let's look at this step by step in more detail. If we can identify a block, and that block has gateways that are only of the XOR or event-based type, and every element is on a path from a start event to an end event, and the data perspective doesn't block any path, so no activities that we cannot reach due to conditions, then the block is behaviorally correct. So notice that here we do not require that there's only one way in and one way out. That is not important for this construct. So if you can identify such a group of BPMN elements, then you can conclude that that group at least is behaviorally correct. And you can combine this with the other, right? So the requirements we had with the previous one was that A and B were behaviorally correct. Now you can use this one and then build that to build your proof. Next, let's look at some anti-patterns. So these are patterns that almost guarantee you a behaviorally incorrect model. It's not a guarantee because they indicate deadlocks or lifelocks, and you can kind of resolve those, for instance, using terminate events. So they are not guaranteed, but nevertheless, if you see one of these constructs in a model that you get in front of you, then it's a big red flag that something might be wrong. So let's look at these patterns. The first one is an XOR split and a parallel join. Now, if no other arcs or sequence flows come in or go out, then the XOR split will produce a token on either the top or the bottom branch. But the parallel join will require tokens on both of these branches, hence a deadlock. So if you see an XOR split and a parallel join that kind of are each other's mirror, then that's a big red flag for behavioral issues. Another anti-pattern is the OR split and the parallel join. The OR split might, based on the data conditions, behave exactly like the XOR, because it is possible that the OR will produce a token only on one of the two outgoing branches. Again, the parallel join needs tokens on both of its incoming branches. Hence, this is an anti-pattern, and unless the data saves you here, it is a deadlock. Another anti-pattern is the escaping sequence flow. Here we have matching gateways, so here we have a parallel split and a parallel join. However, in one of the branches, the token can escape. So if the token goes down here and not towards the join, then the other branch, the token, will get stuck here in the join. So this is a typical pattern. If you see two parallel gateways mirroring each other, and in one of the branches the token can escape, then that's an anti-pattern for, again, option to complete, deadlock. The opposite can also happen. If we have two parallel gateways that are mirroring each other, so one split, one join, and in one of the branches an extra token can come in, that means that if that extra token comes in, that will be in the end waiting for the join. Hence, again, possibility of deadlock. Anti-patterns also exist for data. So in this small model, we have a problem, and that is that the first task depends on the data object, which is produced only by the second task. So in this case, when the first task will fire, the data object will not be there yet. Of course, this is a lot harder to verify or to recognize this pattern in a model, because data objects can be replicated. So there might be other parts in the process model where the same data object is referenced, and if it was produced before the left task of this small example, then there is no problem. So this is a very tricky thing to verify. But a good way to do that is to carefully go through the model and see that every data object is produced by a task before it is required by a task. And notice that if a task requires it and produces it, then it must already be there before the task starts, right? So you cannot say that this task reads and writes from a data object, but the data object is only available from that task. That doesn't make any sense. So the output of a task is that there is an updated data object, but then it still must exist before the task begins. That are some patterns and anti-patterns you can look for within a single pool. For the situation between the pools, the situation is a little bit more difficult, because we not only have what each participant, each pool is doing in their own process, but we also have the communication between them. And as you all know, communication might break down, or people might be waiting for messages that will never come from each other. So unfortunately, for interpool communication, the best way is to play the token game and try to break a behavioral correctness property. Nevertheless, I have a few anti-patterns that you can look for and that indicate common problems. In this first anti-pattern, it is unclear who starts the process. Both pool A and pool B have an empty start event, so that means that the environment determines who starts the process. However, the environment will do this for only one of them. So one of pool A or pool B will start the process. And if that is pool A, then pool A at least sends the first message, but pool B doesn't know yet that a new process instance has to be started. So pool B isn't waiting for this message and nothing is going to happen. So if you see empty start events in more than one pool, that should be a bit red flag. On the other hand, if B starts the process, then A hasn't started its process yet. So B will be waiting for a message from A that will never come. Because BPMN, by definition, starts the process from one start event only. So yeah, once it's started, any further triggering of a start event, of an empty start event, will simply mean that another process instance is started. So don't mix these up. The process must be started by one organization, one pool. A second anti-pattern for interpool communication is data. In this example, pool A produces a data object and pool B needs that data object. But data is limited to the pool it is in. So the fact that pool A has the data available does not mean that pool B also has it available. So this is again a potential deadlock. The only way to transfer information between organizations is using messages or signals. So here the data cannot magically jump between pools. For a third example, this is an anti-pattern of not communicated choices. So we see that pool A is making a decision between the top or the bottom branch, and in the bottom branch a message is sent, this one. Now the problem here is that pool B has to take a decision as well whether to wait for that message or not. But again, the data doesn't magically jump from pool A to pool B. It must be communicated using a message or with a signal. So this decision here, unless it is some shared knowledge, pool B cannot know that pool A took a certain decision. So pool B has no way to know whether to wait for the message coming or to skip it. So I'd wait for a message or to skip it. And that must be communicated in some other way. So if we see a XOR split in two pools with a message close behind it, that's a bit of a red flag for uncommunicated choices. The way to fix this, by the way, is to use an event-based gateway and let pool A send the message with the decision. So you can do that with an event-based gateway and that pool A sends one of either messages. These were some hints for ensuring behavioral correctness in your process models. This is not a full overview, and unfortunately there are some challenges that prevent anyone from coming up with a recipe or an algorithm or verification technique for behavioral correctness in BPMN. And the first reason why that cannot be done is that BPMN has informal semantics. So if you look at the BPMN standard, it's written in text, and that text needs interpretation. And there are maybe some inconsistencies in the text. These things make that it is not yet possible to fully grasp a BPMN model if you're a computer. Second, if you take the BPMN language and you consider the conditions that you can put in and the expressions that you need in order to do that, then BPMN is actually Turing complete, which means that there is no way to study or to prove for a computer that you can always reach an end event, which is one of the requirements of behavioral correctness. So unfortunately, there is no way to do this automatically. However, it can be assistive. So there are tools available that tell you whether the model is adhering to certain behavioral correctness properties or uses some strategies in order to prove for a large class of models that it is behaviorally correct. This wraps up this video on how to ensure behavioral correctness, and I hope that it will help you in order to ensure that the models you create do not have these common issues.